Hello, welcome to our channel for probability and statistics. In this video, we will talk about probability distribution of the functions of discrete random variables. So sometimes in statistics you will need to derive the probability of a function of one or more random variables. For example, suppose x is a discrete random variable with probability distribution fx, and y is the function of x, so we denote ux, which defines a one-to-one transformation between values of x and y. So now we wish to find the probability distribution of y. It is important to note that the one-to-one transformation implies that each value x is related to one and only one value of y from y equals ux. And each value y is related to one and only one value of x. So x can be calculated from y also. We called wy. And wy is obtained by solving y equals ux for x in terms of y. So it is clear that a random variable x, y assumes the value y when x assumes value wy, right? So we assume x is the value of wy. So x and y are one-to-one transformation. So the probability of y, called gy, equals the probability of y equals y, which is also the probability of x equals wy, because they are one-to-one transformation. So there is y has a one value, then it should be x has another value which equals wy. So which means the probability distribution of y equals y is same as the probability of the distribution of x equals wy. So x we fill with the wy, so it is the probability distribution of fwy. Here f is for distribution for x, right? So we just fill in x with the wy for x. So we look at an example. Let x be a geometric random variable with probability distribution. So this is a geometric probability form, the probability of success and the failure. So geometric distribution is that take repeated trial with a success rate p, but you get until you get a first success. So x can be 1, 2, 3, 4, because there can be failure. How many times you get a trial, but one success, the other is a failure. So we times the power of 1 of 4. This is the failure probability. This is the success rate. And the question is to find the probability distribution of the random variable y, which is the x squared. So the solution is, since the values of x are all positive, so x is positive, and the transformation defines a one-to-one correspondence between the x and y value. So one x has a one y, right? Both are positive. And from y equals x squared, we can get x is the square root of y. So we fill in the density. So gy equals, because the one-to-one transformation, so gy is also the density of x with the form of square root of y. So we just fill in the density in the probability function for x, we'll get gy equals 3 of 4 times 1 of 4 with the square root of y minus 1. So here only with the variable y equals 1, 4, 9, 16, 25, and so on. And next we will talk about two-dimensional transformation. Suppose x1 and x2 are discrete random variables with a joint probability distribution f x1, x2. And we let y1 equals u1, x1, x2, and y2 equals u2, x1, x2. Define a one-to-one transformation between the points x1, x2, and y1, y2, so that the equations y1 equals u1, x1, x2, and y2 equals u2, x1, x2 may be uniquely solved for x1 and x2 in terms of y1 and y2. So this is the x1 equals w1, y1, y2, and x2 equals w2, y1, and y2. So the joint probability distribution of y1 and y2, G y1, y2 equals the probability distribution form same as from joint distribution of x, but here we just fill in x with the w1, y1, y2 and w2, y1, y2. So from the probability distribution of the x1, x2 can be used for the probability distribution of the g for the y1, y2, but the value is the reciprocal inverse function of x1 in terms x1, x2 in terms of y1, y2. So which is w1, y1, y2 and w2, y1, y2. Because they are one-to-one transformation. This is very important. And we can go one step further. We get the joint probability distribution of y1 and y2. Then we can calculate the distribution of y1. This is just the marginal distribution of g, y1, y2 by summing over all y2 values. We can denote the distribution of y1 by h y1 is sigma odd possible values of y2 for this function g, y1, y2. This is the joint probability distribution we have shown in the previous page. Then we sum over all the values of y2. Then we get the probability distribution of y1. And similarly, you can get the probability distribution of y2 by summing of all values of y1 for this joint distribution y1, y2, right? Next, we will take a look at another example. So let x1 and x2 be two independent random variables, both having Poisson distributions with parameters mu1 and mu2. And the question is to find the distribution of the random variable y1, which is the sum of x1 and x2. So the solution is, because x1 and x2 are independent, they both have Poisson distributions, so we can write joint probability distribution for x1, x2 is the production of their own probability distribution. So f xy x2 equals f x1 times f x2. So we just fill in the form of Poisson distribution. These two parts to get the result is mu1 plus mu2 minus in power and times mu1 x1 in power, mu2 x2 in power, then divided by x1 factorial times x2 factorial. And for the available value for the x1 equals 0, 1, 2, 3, 4, and x2 0, 1, 2, 3, 4, and so on for all the discrete positive number. So now let us define a second random variable. Say y1 equals to x2. And so the inverse functions are given by x2 equals y1 minus y2, right? And x2 equals y2. So this here marked with red is very important. So we must get the inverse function of x1 and x2 in terms of y1, y2. So in the theorem we have shown before, we can find the joint probability of y1 and y2 to be g y1, y2 equals the joint probability of x1 and x2 just fill with the value of inverse function of x1 and x2 in terms of y1 and y2. So we can see this form filled with the x1 and x2 with the inverse function of these two variables in terms of y1 and y2, right? So this is the joint probability distribution for y1 and y2. And available value y1 can be 0, 1, 2, 3, 4, and so on for all positive integer number. But for y2 is 0, 1, 2, 3, 4 until y1. Because x1 larger than 0, so transformation x1 and equals y1 and x2 implies that y1 and hence x2 must always be less than or equal to y1. So x2, because x1 is positive, so x2 must less than equal to y1, right? Because x2 equals y2, which also means y2 must less than or equal to y1. So that's why the available value for y2 is 0, 1, 2, 3, 4 until y1, right? So we can get marginal distribution of y1. hy1 is just filling all the values of y2 from 0 to y1, because we have shown y2's value, maximum value is y1, right? So we just take summation for all joint probability distribution for y1 and y2 we have calculated in the previous page, summing with the y2 value from 0, 1 to y1, from 0 to y1. So we just fill in and take this part out from the sigma, then go one step further, divided by y1 factorial and then times y1 factorial here. Then we can get this one equals sigma with a combination y1, y2 times mu1, y1 and minus y2, then times mu2, y2. So this part, take a look at this part. This part is the binomial expansion of mu1 plus mu2, so y1 in power. So that's why we can get the result, final result for the y1 is, for the distribution of y1 is minus mu1 plus mu2 in power times mu1 plus mu2 y1 divided by y1 sigma factorial. And the y1's possible value is 0, 1, 2, 3, 4, and so on for integer number. So from which result we can conclude that the sum of the two independent random variables having Poisson distributions with parameter mu1 and mu2 has a Poisson distribution with a parameter mu1 and mu2. So the result is quite interesting because y1 is x1 plus x2, right? And x1, x2 both have Poisson distribution with mu1 and mu2. So y1 also, this is also a Poisson distribution with parameter mu1 and mu2. So for the discrete probability distribution, Poisson distribution is quite interesting. If we sum two independent variables, both having Poisson distribution, then this sum variable will also have a Poisson distribution with the parameter is the sum of these two individual Poisson distributions parameter, right? Thanks for watching.